Okay, in this lecture, we're going to add a new tool to our toolbox of ways to improve our neural network. And we're going to talk about something called batch normalization, which sounds like a very boring thing to do. It doesn't sound very sexy, but in fact, it is one of the most effective ways to improve your neural network. So it's become almost a staple in training very deep models, and it aims to solve the vanishing gradients problem without need for Xavier or other initialization methods. It has many advantages, so much so that it's almost essential for models with a huge amount of layers. So it was introduced in a 2015 paper, and I recommend that you have a quick read of the paper at some point, possibly by pausing the lecture now and having a quick read. It's not very long, I think 15 pages or something. The process is simple. So what batch normalization is just an operation that's added before or after the activation function of each hidden layer. And what you do is you just zero center and normalize the input, then scale and shift the result using two new parameters for each layer. So although this course doesn't focus on the mathematics, let's just have a quick look at the process in a bit more detail, because it doesn't require too much mathematical background knowledge. So X, this is the values from the mini batch, which we're denoting script B, x1 to m, and the parameters to be learned, gamma and beta. So we're trying to output yi, and this is going to be a function of xi. So we set mu b to be just the sample average of the mini batch. Then we also specify the variance, the sample variant of the mini batch. And then we assign this value. This is just like a normalize or a standardization here. And note that we add a very small term here, epsilon, something like 0.0001 or something, just in case this is close to 0 and blows up to infinity. And then finally we assign yi to this value here. And we're learning the parameters gamma and beta. And this is just scaling and shifting. So as you've seen, there's nothing really complicated about this in training, but during test time, we have to take a different approach. So for individual predictions, of course, we cannot use this method. Reason being is you can't really take the sample mean of a single instance or variance or whatever. You can't really do that. Okay, so instead we need to compute the mean and standard deviation at the end of training and use those figures. So it's actually preferred to use a moving average to compute the sample mean and sample standard deviation. And so to summarize, gamma and beta are learned during backpropagation, and mu and sigma, these are estimated using the exponential moving average, and they're estimated during training, but they're not used until test time. So this approach has had a lot of success. So it considerably improves all neural networks experimented with, or almost all, I should say. It almost solves the vanishing gradient problem also. It makes neural networks less sensitive to weight initialization, speeds up learning rates, and acts like a regularizer. Okay, let's talk about some drawbacks. Well, it adds some computational complexity, although it's not too much because we're just doing simple operations. During training time is actually made up for this anyway because it has faster convergence. Okay, let's talk about how we can implement this in Keras, and it's very simple again. we're going to add it before the first layer also. And what you do is you just add it in between each layer like this. So input layer, batch normalization. Hidden layer 1, batch normalization. Hidden layer 2, batch normalization. And then you output. Very simple. So this is all we're going to say about batch normalization, or BN. If you'd like to know more about changing its parameters, such as the momentum for the exponential moving average, then either read about it in Garon's book or look at the documentation for Keras. All right, grading clipping, another tool. And this is the final method we're going to look at that can help solve the exploding gradient problem. And it's called gradient clipping. So what we do is we just cut off the gradients at a certain threshold. This is commonly used in recurrent neural networks because it's difficult to implement batch normalization. This is the code for it here. So within the optimizer, you set the clip value for some number, and then you input this variable into the optimizer. And this will just clip the gradient between -1 and 1. All right. I'll now give you a chance to pause the video and either think about in your head or write down at least 4 advantages of batch normalization that we talked about. Okay, so here are the answers. It considerably improves all neural networks experimented with. The vanishing gradient problem strongly reduced. It actually makes neural networks less sensitive to weight initialization, speeds up learning rates, and acts like a regularizer. You can see why this has become almost a staple in training deep learning models. I'll see you in the next video.